Let's see. Let's try another example. Example 2. This time we will let f, our vector field, be equal to, make it a little bit more complicated, x, y, z, x squared, y squared, z squared, and x cubed, y cubed, and z cubed. Okay, we want to find the flux of this vector field. Okay, let's see. And what surface do we want? Well, let's, let R be the region. So this time the region is going to be defined by several equations in x, y, and z. Be the region z is greater than or equal to 0, x is greater than or equal to 0, y is greater than or equal to 0, and the relationship between x, y, and z is x plus y plus z is equal to 1. So when you put all of that together, what you have is this following region. It is the pyramidal region in the first octant. So let me draw it over here to give myself some room on the left. So there's that, there's that, there's that. Basically what you have is this. This is y, this is x, and this is z. So what you have is that little pyramid right there. This pyramid made up of the yz plane, the zx plane, the xy plane, and this plane, that surface, that's the x plus y plus z is equal to 1 plane. So you basically have a surface, a volume that's contained by 4 surfaces. So you have 1, 2, 3, and 4, the plane. So if you wanted the flux of this vector field, you have to solve 4 integrals. You have to find 4 different parameterizations, and you have to solve 4 integrals. Fortunately, we don't have to do that because we have the divergence theorem. So we can just solve one volume integral. This volume is very, very easily extracted. Okay. So let me actually label these. So this is going to be surface 1, just so we know. This is going to be surface 2. This is going to, the back is going to be surface 3, and of course this plane right here, this thing, we call that surface 4. So again, our surface is the union of all these surfaces, S3 union S4. So if we wanted the integral over this, we have to do 1, 2, 3, 4 integrals. We don't want to do 4 integrals. We want to do 1. The divergence theorem is the perfect tool for this. Excellent. So let's go ahead and calculate the divergence. Let me rewrite f so we have it on the page. So we have x, y, z. Whew, gotta slow down here, get kind of crazy and excited. This is great stuff. X squared, y squared, z squared, x cubed, y cubed, and z cubed. So the divergence of f is equal to, well, so this is f1, this is f2, this is f3, so df1 dx is going to be yz. df2 dy is going to be 2x squared y z squared. And as always, I hope that you are confirming this for me because I do have a tendency to make lots of arithmetic mistakes and differentiation and integration mistakes. And the derivative with respect to the third one, z, is going to be 3x cubed y cubed z squared, if I'm not mistaken. Okay, so now we need to, so now that we have the divergence, so we have the integrand, right? We're looking for this. Divergence of f dx dy dz. We've just found the divergence, so we've taken care of that, the integrand. Now we need to figure out the upper and lower limits of integration for this particular region. Okay, x is going to go from 0 to 1. In other words, it's going to go from here to here. Y, well, the relationship between y and x, y is going to be this height right here. It's going to go from 0 all the way to minus x plus 1. That's what this line is right here. If I take the xy plane, this line is minus x plus 1, or 1 minus x. So y is going to go from 0 to minus x plus 1. So I've integrated in the x direction. I've integrated in the y direction. Now I'm going to integrate in the z direction. Well, this one is easy. Z goes from 0 all the way to, well, here's the relationship. Just solve this for z. Right? It's going to go from 0, which is its base, all the way up to the plane here, this surface. Minus x minus y plus 1. That's it. So again, all of these integrals ultimately come down to two things. You need to be able to extract the integrand. You need to be able to figure out what the upper and lower limits of integration is, and you're done. The rest is very, very easy. That's what this problem, with all these problems, are about. So our flux, our integral, is equal to 0 to 1, 0 to minus x plus 1. We'll do y next. 0 to minus x minus y plus 1. And we have our divergence, which is this thing right here. We have yz plus 2x squared yz squared plus 3x cubed y cubed z squared. And we did dz, dy, and dx, because this is z, this is y, and this is x, working our way out. And when I put this into mathematical software, I get some odd number, but it is a number. 4733 divided by 55,000, or actually 554,000. Sorry about that. You know what? No commas. I'll just write out the numbers. How's that? 554400. Again, we have a positive divergence. It's a very, very small number, but it is a positive divergence. This vector field is actually, if this were a fluid field, the fluid is leaving this volume. It's actually flowing across the surface. That's what's happening. That's what we're measuring. We're measuring the extent to which the vector field is moving out or moving in. That's all we're doing. Okay. So, again, what all of these integral theorems are doing is they're establishing relationships between line integrals and area integrals, surface integrals and volume integrals. They're establishing a relationship between a region in a particular dimensional space and the boundary of that region. This is very, very, very profound. It's the reason it's called the fundamental theorem of calculus. It is absolutely fundamental. You have established a region, you have established a relationship between a region and its boundary. There's no reason to believe that such a relationship should exist. But not only does it exists in any number of dimensions. That's extraordinary. There's nothing really new here. We've just kicked up one dimension. The only difficulty is the mechanics, being able to extract the region, the upper and lower limits of integration. Usually finding the divergence is a very, very easy thing. Finding the curl is actually not that difficult, just slightly more notationally intensive, but again, also very, very simple. So that's it. Sometimes, if you're looking for a particular integral, you'll actually have to solve the surface integral. Maybe you're going to deal with a region where the triple integral, once you find the divergence, is going to be too difficult. So in that case, you have to do the double integral directly. And you might have to integrate over one surface, maybe two surfaces, maybe 3, 4, 5 surfaces. Again, this is where mathematical software comes in very, very handy.